Yeah.
It's always your decision as to what to work on.
So I'm not sure if you want. I can probably do it on my phone, but there's this website that we use for our homework.
Okay. If you want, I can go to that website, pull it up, and we can both be looking at the problems. But you're going to have to send me the URL address, the username, and the password.
Okay. Just usually it comes with a CPM homework help.
Can you copy and paste it into the chat window?
The chat window.
If you look at the GoToMeeting control panel, there's a chat window.
Yeah.
It says enter your message. Well, copy and paste your link into that spot and then hit enter, and it shows up in the chat window and I can bring it up.
Okay.
There you go. Now I'll click on that. And I might also still need the, doesn't look like it. I don't need a name and password.
No.
Okay, where do I go?
Chapter 7.
Should I save this? Let me save this for future reference.
Okay.
Just so you won't have to always put it in the chat window. Which one of these?
7.1.2.
Okay. Gave me an error.
Yeah, I noticed.
Origin is unreachable. Let me back up one step. And let's just try chapter 6, see if that's reachable. That worked.
Hmm.
What was it? Chapter 7, 1.2?
Yeah.
Let's try it again. It might have just been a glitch. It was. Just a temporary glitch. Now what do I click on?
Number 7-15.
Okay. The first question is probably the most important question you can know. Believe it or not. And that is the dimensions of these two triangles. These two triangles, they've been teaching you about them for 3 years. And what's vital is to know their dimensions. Okay, we know they're right triangles. One's a 30-60-90 and the other's a 45-45-90. Well, I call them the unit right triangles because the side opposite the smallest angle is always 1. Side opposite the 60-degree angle is √3 and the hypotenuse is 2. On the 45-45, it's 1, 1, square root of 2. Memorize this so you can recreate it from your brain at any point in time.
Okay.
Okay?
Yep.
There's nothing you could memorize in math as important as these two triangles. It's the foundation of trig. It's the foundation of geometry. So, do you see where I labeled the other sides? In other words, the side opposite the 60-degree angle is √3 and the hypotenuse is 2. They labeled one of the sides for us. The side opposite the 30-degree angle was 1. I intentionally drew this with a different orientation just to impress upon the need to memorize these two triangles. Not the two triangles so much as what their dimensions are. Because this is the root of trig. Have you had any trig at all?
No.
Not even in geometry you didn't have some trig?
Maybe.
Okay. Well, this is the foundation of all your basic trig functions. The sine of 30 degrees is 1/2. Cosine of 30 degrees is root 3 divided by 2. The sine of 45 degrees is 1 divided by root 2. That's why these two triangles are so important.
Okay.
And when it says label the missing sides with their exact lengths, that means they do not want a decimal answer. A decimal answer is an approximation. It is not exact. The exact length is square root of 3 and square root of 2 in this triangle. It's not 1.71, which is the approximation for square root of 3, or 1.41, which is the approximation for square root of 2. So that's what they mean when they say leave your answers in radical form. That's the exact answers. And I've labeled both triangles. So that's A. Now, B. It's sometimes called a half equilateral triangle. Why? Well, if you were to take an equilateral triangle, what's the measurement of all three angles?
60.
And then if you drop a vertical from any vertex, you end up with a 30, 60, 90 triangle. In other words, this triangle right there is a 30, 60, 90, which is the same triangle as that one. And that's one of the reasons that makes it so important, is that it is half of an equilateral triangle. And equilateral triangles are very common, so you end up with 30, 60, 90 triangles that are also very common. Now, part B of 715. Well, if I know my hypotenuse is 2, I know this side is 2, and this it's half of 2, so that's 1. Now I can use the Pythagorean theorem to figure out that that's root 3. Okay? So that explains how half of an equilateral triangle can come up with the missing dimensions that we needed in part A. Because the one thing, let me go through it once again. The one thing you know about an equilateral triangle is all three sides are equal, right?
Yeah.
Those are all 2. Well, when you drop a vertical, that splits the bottom, so now that's 1. Now you have this triangle that's the 30-60 triangle. The side opposite the 30 is 1. Side, the hypotenuse is 2. If you do the Pythagorean theorem, that's root 3. So by looking at it as an equilateral triangle, I was able to come up with these dimensions if I didn't know them already. But trust me, there is nothing you want to memorize more important than those dimensions. How do I get to the next page, Nicholas?
You click on Show Lessons.
it as 716. Okay. Now, am I supposed to be putting answers into these as we go, or is that not necessary?
No, it's not necessary.
Okay. So this isn't like some programs where you have to put the answers in exactly as they want it, which makes it really hard. All right. So let's look at this triangle. And what we really want is the measurement of theta, right? When they say find A, they mean find theta. Clear on that?
Yeah.
Well, what trig function relates 0.3 and 1? That's what we need. Is it sine, cosine, tangent, secant, cosecant, cotangent?
Sine.
So I can say the sine of theta equals what?
0.3 divided by 1.
Which is just 0.3. So theta equals what?
17.4.
Hold on. How do you do it? I don't care about the answer. I really don't. How do you figure out theta?
Yeah.
You take the inverse sine of 0.3. In other words, notice what we have here. We have the sine of an angle equals a number. Well, if I take the inverse sine of both sides, then the left side becomes just theta. If you have the inverse sine of the sine, you're left with theta. But if I take the inverse sine of the left side of that equation, I got to take the inverse sine of the right side also. So you end up with theta equals inverse sine of 0.3. What is that number?
17.46.
Is that in degrees or radians?
Degrees.
In other words, you have to know what your calculator is set on. What kind of calculator do you have, Nicholas? Is it an Inspire or a TI-84?
84.
You know whether you're in degrees or radians?
Yeah.
Okay. Because it matters a lot. In other words, your answers don't look anything close if you're in the wrong unit. In other words, you have to know whether your calculator is set to degrees or radians before you do any trig problems. All right. So that angle A is 17.46 degrees. What's angle B?
I don't know because it didn't really ask us to.
Well, what's the I know, but I'm asking you because it's important. What's the relationship between angle A and angle B? What do they have to add up to?
90.
Yeah, that means angle B has to be 72.54 degrees. All right. So I guess I want to go back and how do I go back? It won't let me click on show lessons.
Huh.
Let me try going back to this. That was chapter 7. That was 1.3, right?
0.2.
Okay, let's look at 1.3 and 36. Are we done with 7.2 or did I cover all the problems that were in that? Do I need to go back to it?
Yeah, you go back to it.
In other words, there's more problems than 7.2 that I didn't get to. Which one of these do I want to click on?
The 7.1.2.
And then 715? No. Did we do 715?
Yeah, we are on 717.
Okay. All right. Where do you go to school, Nicholas?
Thunder Ridge.
The only reason I ask is because all of a sudden they're mixing up trig with Algebra 2.
It's a combined class Algebra 2 trig.
Oh, okay. Yeah, that's fine. I got no problem with that. X and Y intercepts. If I want the Y-intercept, what do I do?
You put X in for 0.
Good. So what does the Y-intercept equal?
-10.
That's the easy one. If I want the X-intercept, what do I do?
Put 0 in for Y.
Okay, so I solved this equation, and notice that just I got to solve something. I didn't have to solve anything for the Y-intercept. I just had to look at what the constant was. Okay, but to solve this, I need to factor it. Does that factor?
Yeah.
To what?
2x plus 5 and x minus 2.
Good. So if that's equal to 0, what are my solutions?
2 and 5/2.
Minus 5/2. Right? In other words, the way you solve this is you set this equal to 0. First thing I do is subtract 5 from both sides. Next thing I do is divide both sides by 2. So there's your second solution. And X-intercepts are minus 5/2, comma 2. There's 2 of them. And that makes sense if you think about it, because when you're looking at a quadratic, it does this. It's a parabola, right? So
Yeah.
there should be 2 X-intercepts if it goes through the X-axis. And we found 2. We got minus 5/2 and 2. So that's how I would graph that. And we also had a Y-intercept of minus 10. So that's minus 10. All right, let me go. It does not like me clicking on that. I guess I got to go backwards every time. So this is 717. I want 718, which is still under 7.12. All right, I think I understand now. No calculator. What's the log of 1 equal to? First of all, what's the base of this?
10.
Okay. What is that equal to?
0.
Yeah, and the way I usually tell, I don't know how you do these, but the way I do them is I make up a variable, x, I put it over there, and then I convert the whole thing to exponential. In other words, I know that 10 to the x has to equal 1. Well, the only x that works is 0. Any number to the 0th power is 1. Therefore, the log of 1 is always 0, no matter what the base is. If I would have said, what's the log base 7 of 1, the answer is still 0. The log of 1 is 0. Memorize that, because you're going to need that a lot. Now, let's look at the second one. The log of 10 to the third equals what?
X.
Okay, that's a good start. Now put it into exponential expression. What's the base of this log?
10.
Okay, so I'm going to write a little 10 there. Now put it into exponential.
10 to the x equals 10 to the third.
Right. So what's x got to be?
30.
There you go. The next one, 10 to the log, natural log of 4. Well, do you think how to explain this for a second? If I said x, then that doesn't help much in the explanation. Let me say this. B to the log base b of x is always equal to x. Okay?
Okay.
And notice that's our situation here. We have 10, which is my b, to the log. Well, what's the log? The base of that? It's 10. So the b's are the same, which means the answer is 4. Always. In other words, this is always true no matter what b is. B to the log base b of x is always equal to x. If I said b to the log base b of 17, that's equal to 17.
Okay.
Okay, that's just another little log rule that you want to remember. All right, let's look at the last one. 10 to the... Now, this one, it's useful to do something with that 3 other than leave it where it is. What should I do with it? When you have a leading coefficient in front of a log expression, that coefficient can become an exponent, like that. See what I did?
Uh-huh.
Well, now that is 10 to the log of 64. What's that equal to?
64.
Okay. Using that rule we just learned from the previous problem. Okay, that was 718. Now, when you see an expression like we are looking at here, where you got the numerator as a quadratic that looks like it's factorable, and you got a linear denominator, what's our first step?
Factor the top.
Okay, factor the top.
X plus 5, x minus 1.
Notice that the top has a factor that matches the bottom. That's on purpose. That means this whole thing is equal to x plus 5. But there's a hole. Where's there a hole? At
I
x
don't.
equal what?
X plus 5.
1. Why? Because the number one rule of mathematics is thou shalt not divide by 0. Okay? Well, if x is equal to 1, that means I would be dividing by 0. Despite the fact that x minus 1 canceled in top and bottom, and I was left with this. Well, there's nothing about x plus 5 that looks like x can't be equal to 1. But the domain restriction holds, and it holds as a whole. In other words, if I were to graph this function, I would graph x plus 5, so I would start at 5, have a slope of 1, but then I would put a hole at x equal 1, because x can never be 1. If x is 1, you're dividing by 0, and you cannot ever divide by 0. So the result is you don't just get a straight line that looks like x plus 5. You get a straight line with a hole there. Now, there's something interesting about holes, and that is that if you put this original function into your calculator, you will not see a hole, because the hole is infinitesimally small. It only occurs at x equal 1, which is just one of an infinite number of points on the x-axis. So your calculator sees a hole, but it's so tiny that it doesn't show up when you graph it. In other words, the graph of this function on your calculator looks very much like the graph of this function. You can't tell the difference on your calculator. But there is a difference. This function right here has a hole. X can never be 1. Whereas this function over here on the right doesn't really have a hole. There's no hole there. But if I'm going to graph this function on the left, I've got to allow for that hole. Now,
Okay.
to fill out the table, let's do it. Our function is x plus 5, and x can never be equal to 1. That's our function. So now let's fill out the table. If I put in minus 2, what is f of minus 2?
3.
So that's what goes in the y spot. Okay, you understand that f of x is the same as y.
Yeah.
Okay, what's f of minus 1?
4.
What's f of 0?
5.
F of 1?
6.
F can never be minus. F can never be 1. So it does not exist. You see why?
Yeah.
In other words, because of that restriction on the domain, x can be anything at all except 1. So when they tell us that x is equal to 1, well, x can't be 1. Therefore, I do not have a y value. It is not 6. The reason it isn't is because there's a hole there. When x is 1, y isn't 6. Y does not exist. There's no y value when x is equal to 1, because x cannot be equal to 1. Now, what's f of 2?
7.
And what's f of 3?
8.
So there's your table. And the only one that's weird is the when x is equal to 1, y does not exist. Y, what kind of function is it, first of all? The black line that I've drawn, it's linear, exactly. Well, that's what kind of function it appears to be. What is not correct about connecting all the dots? It's not linear, it's not continuous. In other words, the definition of continuity, which you're getting to, but the definition of continuity is, can I draw the graph without lifting my pencil? Well, I cannot draw that black graph without lifting my pencil. I got to lift my pencil to draw the circle. Actually, I suppose I wouldn't have to, huh? In other words, I could draw it like this. Ooh, that's why that definition doesn't always work. That is the layman's definition for continuity. It is not the mathematical definition. But I think you understand what I'm saying.
Yeah.
In other words, you would have ended up with a bunch of dots, okay, based on this table. In other words, f of minus 2 was 3, f of minus 1 was 4, f of 0 was 5, f of 1 did not exist, so it was a dot, f of 2 was 7, and f of 3 was 8. Well, notice I cannot just draw a line through all of those dots because I've got a hole at 1. So I can draw a blue line to that part, then I put my hole and I draw a blue line to that part. So it appears that I have a straight line, but what I really have is a straight line with a hole at 1. That's why you cannot connect all the dots, is that it's not a continuous straight line.
Okay.
Look for a simple pattern for the values in the table. What appears to be the relationship between x and y?
+5.
It's linear. That's the answer they want. It's linear. In other words, when I give you an x value, you give me a y value, and the resultant graph is a straight line, almost, with a hole in it. What is f of 0.9?
5.9.
Good. What is f of 1.1?
6.1.
Okay. What appears, let's see, add the points to your graph. Okay, I get that. Is there an asymptote at x equal 1?
No.
No, it's not an asymptote, it's a hole. And there's a difference. There's a big difference. Let's talk about asymptotes. If I gave you a function y equal 1 over x, well, that has some asymptotes in it. Has an asymptote at x equals 0, and also has an asymptote at y equals 0. Asymptotes are pretty clear, and that is that as the black line approaches 0, it goes to infinity or negative infinity, depending on which side of the y-axis it's on. Okay, so asymptotes have that characteristic, that when you're approaching vertical asymptotes, you're going to infinity. Well, that's not what our curve is doing. Our curve is merely a straight line with a hole in it. It doesn't have asymptotes. It was x plus 5. So it's a straight line that has a hole at 1. It's supposed to be a straight line. But there's no asymptotes. Simplify the formula. What do you think the complete graph looks like? Well, we already simplified it. We got y equal x plus 5 with the one provision that x could not be 1. In other words, that's the answer. It's not just y equal x plus 5. Because the two are not the same, notice. Y equal x plus 5 is a continuous straight line. Y equal x plus 5 with a hole at 1 is different. It's the same straight line, only there's a hole where x equal 1. All right. Isn't this the same problem? I believe it is. We figured out that x of minus 2 is 3. Does this do any good? I mean, for you, does it do any good for me to figure these out or to indicate what these are?
It's not really necessary, no.
All right. Because I don't know how to write does not exist for 1. So I won't continue on here. Back up. I guess we're on 7.1.3. Now I do kind of find it interesting that you're at a Highlands Ranch High School and they're kind of doing integrated math, which is unusual. Most of the Highlands, or most of the Highlands Ranch High Schools teach math the way most everybody else teaches math, which is when you're on Algebra 2, they do Algebra 2. When you're on Trig, they do Trig. Whereas a school like De Evelyn teaches integrated math, where every single year, whether you're 9th grade, 10th grade, 11th grade, or 12th grade, they give you a little bit of algebra, a little bit of geometry, and a little bit of trig. So it's a completely different way of teaching. And so far, we've seen Algebra 2 problems and trig problems. So the curve we're looking at here, what curve is that?
A sine wave?
Yeah. And that's what it says in the premise, is this s of theta, meaning s as a function of theta, is equal to sine of theta. And that is a sine wave if I ever saw one. It even goes to 360. In other words, the curve that we're looking at is the curve that they're talking about. It's this function right here. Passenger gets on initially. At what point?
0.
0, 0. In other words, when the angle is 0 degrees, s of theta is also 0. Passenger reaches the bottom of the water pit where?
At 0, 270.
270, 0. Just reverse. In other words, your x coordinate goes first, comma, your y coordinate. So it's 270 And it's not 0, it's comma minus 1. See that? And that's why they say he reaches the bottom of the water pit. In other words, these sine functions or cosine functions can be described or can be used to model all kinds of things in real life. You could talk about a water pit ride or a roller coaster or even a circular, what are those called? The things that just go round and round?
I have no idea.
You know what I'm talking about?
Yeah.
Okay. All of those can be described by these sine functions. And when you get on one of these things, let me draw it. Here's the ride. Well, let's say they have steps up to here. And you get on right there. Okay? And the thing is going that direction. Well, what are you doing? You're getting on at the middle point and going up. That's a sine function. That's what a sine function does. It gets on at the middle point and goes up. And then from going up, it does nothing but goes down all the way to there. So that's your low point. That's minus 1. And then it comes back up to the middle point. Okay? So this ride that's a circular ride can actually be described as a sine function perfectly. Now, what if I change it a little bit, and instead of being up on stairs, you get on down here? In other words, here's our stairs, and here's the person getting on. Now they get on the bottom, and they do nothing but go to the top. What kind of function is that?
I don't know.
That is, notice what the cosine function does. Gets on at the top and then goes to the bottom. So this would be a negative cosine function. In other words, it would be symmetrical with the x-axis. It would just be a reflection. Notice that here, I get on at the bottom point, and I immediately go to the top point, just like this person. So if I was trying to describe this ride to the person getting on at the bottom, I would say use a negative cosine curve, because negative cosine curves start at the bottom and they go immediately to the top and then they go back to the bottom. Well, that's what he does. He starts at the bottom, goes immediately to the top, and then he goes back to the bottom. So these sine and cosine curves can be used to model 1,000 different things. The tides, your breathing, the temperature based on the date, taking an amusement park ride like this, anything that is periodic in nature. And all of those things I just described are periodic. The tides are periodic. Every 12 hours the tides come in and then they go out. And then 12 hours later they come in again. And then 12 hours later they go out. So, and it's just like you're breathing. It may take you 4 seconds to breathe. In other words, you take a breath, you hold it for a couple seconds, you breathe out. 4 seconds passes between when you take breaths every time. That's a sine function. That's a function that looks just like this. You're breathing. Musical notes are sine functions. Musical notes are like that. And the difference in the musical note is the difference in the period length. So the difference between a C and an E is a tighter frequency. In other words, one might look like that, whereas one would be spread out like that. The only difference in musical notes is the distance between their peaks.
Okay.
Interesting. What are we supposed to do with the rest of this? Anything at all?
I don't think so, no.
Alright, so we'll just back up and go to the next problem. In other words, I think we kind of answered all of these problems in our discussion of this function already. In other words, by answering A, B, and C, we've answered all of these parts down here. And I suppose if you were doing this all on your own, you might answer certain things down here. But in a tutoring session, we don't necessarily need to do that. All right. We've already said that if we were on this ride called the Screamer, and it models this sine function, then we have to be getting on right there in the middle. That's the only place that would model a sine function. So they've built some stairway up so that you can get on in the middle of the ride. All right?
Okay.
All right. Let's look at this position right there. What is your height? Can you see where my cursor is?
Yeah.
What's the height right there?
0.
Okay. What's the height at 90 degrees?
1.
That's 90 degrees right there. So that's the maximum height of that Ferris wheel. Now, when you hit 180 degrees, why did they do this? Wow. Notice that A is not exactly at the peak. It's a little bit beyond it, right?
Mm-hmm.
So really where A is right about there. Notice that B is not there. B is a little bit beyond it. It's right there. C is all the way back to our starting point. So that's A, that's B, and that's C. And the Ferris wheel does exactly what the sine function does. It starts out in the middle, goes up to a peak, comes back down to a middle point again, keeps going down to a low, and then comes back up to the starting point. It's exactly what that sine function does. So I guess the answer to 7-37 is that A is right beyond the peak. some point below the peak. Where exactly, we have no way of determining because they don't label A. If that was 92 degrees, we could look up what the sine of 92 degrees is and have an answer. But they didn't label A. It's just clear that A is slightly to the right of our peak. And that B is not the middle point. B is slightly to the below the middle point. So that's why B is there. And again, we can't really put a number on that because they haven't given us the horizontal coordinates of that point. I mean, is that 200 degrees or 210 degrees? Who knows? They didn't label it, so they don't expect us to give them an answer. The only answer we can give them is that A is beyond the peak, B is beyond the middle point, and C is back to the point we got on. And that's the only answer that makes any sense for this problem. 737. See, most of these problems are trick. There's the tree. Okay? I'm going to let the height of that tree be h. And Julie's trying to measure the height of the tree, and she notices that a 3.5-foot post near the tree casts a 4.25 point shadow. So that's 4.25 right there. And she notices, well, the sun's in the same position, right? The tree shadow is 100 feet. So we have similar triangles. How tall is the tree? Give me a ratio that tells me how tall. In other words, once I realize that I have similar triangles, and the reason I do, Nicholas, is because the sun is right there, right? Mm-hmm. For both. In other words, the sun is in the same position in the sky. So this tree is going to cast a shadow that's dependent on where the sun is. Just like this post casts the same shadow depending on where the sun is. That's why these two triangles are similar. Now, the fact that they're similar allows you to calculate h. What ratio has to be true? Divided by what?
Divided by 3.5.
Okay, I'll go with that one. Equals what?
100 divided by 40 or 4.25.
Yeah, and that gives you h. So h is equal to 3.5 times 100 divided by 4.25. Whatever that number is. If you have a calculator, go ahead and come up with it. I don't really care. In other words, I am never interested in the final answers. I'm only interested in how you set it up. Understand?
Yeah.
Well, notice that there's another way to set this up. In addition to h is to 3.5 as 100 is to 4.25, I could also say h is to 100 as 3.5 is to 4.25. And notice I get the same answer regardless. In other words, when you're dealing with similar triangles, all of the ratios are true and valid. That's the same number I got when I did it the other way. So when you have similar triangles, the most important thing to remember is that corresponding sides have similar ratios. In other words, h is to 3.5 as 100 is to 4.25. But also, within this triangle, this ratio, h is to 100, is the same as 3.5 is to 4.25. So it's not just one way that the ratios work. They work in virtually any way you want to put them. When you're dealing with similar triangles, that is the truth about ratios, is that you can do it pretty much any way you want. I think that we did 7.38, right? Yeah. Okay, jumping around again. In other words, jumping from trig and algebra to precalculus. So your school is kind of following an integrated math. It's kind of late, but let me just do problem A. I do have an 8 o'clock that I have to get to. The log of 6 is equal to the log of 2 times 3. You see that?
Yeah.
Well, the log of 2 times 3 is equal to the log of 2 plus the log of 3 by the rules of logs. In other words, that is the same as that. When I am multiplying inside the argument, it's the same as adding two different log functions. And then they tell us what the log of 2 is. That's 0.301. And they tell us what the log of 3 is. That's 0.4771. So I can add those two numbers together and I get 0.5072. That's what the log of 6 is.
Okay.
Okay? And you just have to know your rules for logs. Let me just go over the 3 primary rules for logs in the last 2 minutes here. The log of two numbers being multiplied together is the log of the first number plus the log of the second number. The log of two numbers being divided, like that, is the log of the numerator minus the log of the denominator. And the log of a number that is being exponentiated, like that, is the exponent times the log of that. So those are the 3 most important rules in logs. You absolutely need to memorize these. I'm being totally honest with you, Nicholas, when I tell you what you need to memorize and some things you don't need to memorize. When I tell you you need to memorize this, take it to heart. You need to memorize this, these 3 rules. Not only do you need to memorize them, you need to be able to go both ways. You not only need to be able to go that way, but if they give you 2 log equations like that, you need to be able to put it back into a single log equation like that. In other words, if I told you I had the log of 2 plus the log of 3, I would know that that's got to be equal to the log of 2 times 3, which is the log of 6. So if I wanted to know the log of 6, all I got to do is look in my calculator what the log of 2 is, add it to the log of 3, and I got the log of 6. Now I could also look up the log of 6, but the whole point of this problem is to teach you those 3 rules.
Okay.
Okay, and these 3 rules are the nuts. You need to memorize those 3 rules to do all of these problems. All right, Nicholas, I'm going to let you go. I will talk to you next time.
Okay.